So today we are continuing our discussion on this non-parametric approach for um, applying this Bayesian inferencing, which means for the Bayesian inferencing, we would like to compute the probability uh, density function or probability densities at a point. We have already seen that in naive-Bayes classifier, which is the example what we have considered there in the naive-Bayes classification example. It was an example of a non-parametric estimation. We did not consider any parametric um, distributions, any kind of density functions with certain based on certain parametric description. So we'll see that how that method is extended for the continuous random variable. So in that case, if you can remember that the naive-Bayes classification example, we have considered our attributes, they are assuming discrete values. So simple counting of the values over the frequency of each attribute value can give you the estimation of probabilities, whether it is a marginal probability distribution or whether it is distribution. So that is easily computable. So the similar concept we can consider for the continuous in the continuous domain also. So we'll start with the simple case of univariate random variable, and here you can see that I have considered n observation points of that random variable, and we would like to compute the probability density of this variable at its particular value of x. Now, one of the key principle here that we would like to compute the probability density value. So it is not exactly the probability at a point. It's a density within an interval. So that is what is our objective to compute. And there, it can be simply extended if we use the concept of cumulative probability distribution. That means, so the cumulative probability is defined when you consider that the probability of the random variable within certain bound. That is the kind of cumulative distribution. So here the example is given. It's a coded way I have represented. This hash means number. So number of instances when the sample value is less than the value x, when you are estimating the cumulative probability at a point x. And since there are total number of observation is n, so your cumulative probability is given by the simple definitions of the frequency-based definition of probability. So number of samples less than x, and that is what is your cumulative probability distribution. Sorry, cumulative probability at x. Do you have any question here? It's the basic definition. It's very fundamental, and from this this base definition, we'll see that the whole concept, whole theory has been developed. So if you have any query or any questions, let me know. So then, how do you compute the probability density around x? So since we have the cumulative probability at a point x, so we can always consider what is the difference of this cumulative probability within an interval centering x or around x. So this is the definition that we are considering probability density. As you can see in this definition, it is the cumulative probability at x plus h minus cumulative probability at x. Then you are simply divided by the width of the interval h. That is what is your density. Do you agree? This expression? Any doubt? So careful that this divisor n, that is the number of samples. So it is a common divisor of the cumulative for computing cumulative probability, right? For both at x plus h and x. So now there is another estimation. Instead of considering x is one extreme point of the interval, here it is the lower extreme point of that interval, we may consider x is the central point. So which means you consider both at the upper end and at the lower end around x. So x plus h by 2 and x minus h by 2. So instead of observing the cumulative probability of at x, we observe rather cumulative probability at x plus h by 2 and cumulative probability at x minus h by 2. And then you take the difference and you divide by h. That would give you also an estimate of x. The same probability density, only it's a different estimator, and which is more robust because it is also taking care of the other side of the observation. So in that way, it is considered to be more robust. Now, as you can see that actually this cumulative probability distribution can give you a histogram. The definition of histogram of a bandwidth h means you are partitioning your domain in the intervals of h, and then you are observing that how many times a particular value occurs, how many times the random variable occurs within that interval. So that is what is histogram. Is it clear? That is what actually cumulative probability can be computed from the histogram itself. So if we compute this histogram of bandwidth h, then this density can be also defined from the histogram using this simple definition that how many times a random variable occurs in that bin. And of course, since you are estimating the density function at x, you have to find out that bin which contains that x. And then you get the probability of that interval, and then you divide by h to get the corresponding density value.
So x is the middlemost value.
X is the no. X is here in the concept of histogram, x is an element of that interval. It is nothing to do with the middlemost. So there are different kinds of estimations. So naive estimator, where actually you are considering x is the middle value. So each definition will give you a different value with the same data set. You can use any one of these. I hope this is clear.
Yes, sir.
Right? So they are not giving you the same value. Please remember, they are all estimates. So they would be close, but they are not exactly the same. They are not equivalent in computation. Now, one of the advantage of this histogram is that the training sample, see, once you have computed this histogram, then for estimating this probability density value at any point of the random variable, at any value of the random variable, you do not require the training samples further. Only the histogram is sufficient. Okay, so this is one of the advantage, if you make it an histogram-based computation. So we can further refine this particular estimate of these density functions if we use a kernel function, and its kernel actually gives some kind of weightage over the over a short interval around any occurrences. See, the idea is that, say, you are basically counting number of observations when at a particular value of x. But whenever some random variable occurs, some observation is there, there is a noise involved in it. And also you can consider that no, the observation could be within that point. Say if you observe a value, say for example, at x equal to say 5. Now exactly there are experimental error and many other things. So it is, so if you just simply count based on that x equal to 5, maybe that is not very much robust. So why don't you consider that the observation could be, so expected value could be 5, but around that there is always a probability that these values could be 5 or 4.9 or 4.8, whatever. So the kernel function, it is trying to provide you some kind of weights of these observations around that value. So it is giving a predetermined, it's a function for any occurrence at a particular value. It will simply centering that value, it will provide a weight around that neighborhood, and it is a sum total of that weights can give you the strength of evidences of the occurrences of random variables around that value. So instead of taking simply the point observations, we are just considering every observation within certain interval of uncertainty around that point. So that is the motivation when you use this kernel function, and we can just simply put this under the same framework of estimation of density functions. We can see only thing is that instead of having a single value for every occurrence as single weight like 1, so every occurrence you count it like 1 means you are giving simply weight 1 to that at that position of the occurrence of the random variable. We will be distributing that 1 weight in this interval so that the sum of the weights within that interval still remains 1. So total number of if I integrate over all weights for all observation, it will be still n. But no, we can better manipulate with mathematical expression. So you'll see that. So again, we are considering this, and we, as I mentioned, that if there is an observation at a point x superscript t, right? That is the observation point. Then we assume around that interval, so d x superscript 3, it is basically the distance. So it's a kernel is a function of that distance. So the idea is that in this function, as the distance increases, this weight will be decreasing, and the weight will be maximum at the when the distance is 0. That means at x equal to x superscript t. Okay. So which means if I consider the special case what we discussed earlier under this kernel estimator, the function, this function is very simple. Can you tell me what is this function in that case? That previous the estimators what we have used. If I consider a kernel function for those estimators, what should be the form of that function?
Something like a box function with equal weight.
Yeah, I mean, that is, you are considering interval. I'm talking about the previous estimators, like these estimators, what you have used.
Maybe uniform 1/n weight for each.
Actually, it is 1 at x superscript 3 and 0 for any other value. Because you are counting only that, you are taking an effect of observation, effect of that occurrence is only at that point only. You are counting only that. You are not really spreading its effect in its neighborhood. When you are just simply doing the frequency count, cumulative count of observations in that definition, or histograms, right? But when you are using kernel function, so that is a special case of kernel functions. But that is what we are going to do now. We are going to spread this weight around its interval, and we'll take into account of that factor. So kernel estimator, actually this window, this interval is called Pearson window, and you can have different kinds of kernel functions, and I will give you some of this form. So we can also express these kernel functions in this form. That means it's a function of, you see that x minus x superscript 3, which is showing that how far is x from x superscript 3. I mean, it will be, you can see that since it's distance function, this has to be symmetric over xt. And also it is divided by h. H defines as width of the interval. So the kernel, so the property of this function should be that if I integrate this kernel function, it should be equal to 1, right? If I integrate it, it should be equal to 1 over that point. And you are considering, so this is one kind of kernel function, as you have said, that something like box function. It is a box function, as you can see that it is a normalized way of representing. So if you vary h, the width of the box will vary, right? It's a normalized representation where h is considered as 1 in this case, but you can have any. U is represented in the normalized form, as you can see. And you can have also Gaussian kernel. So this is also a Gaussian kernel where you have almost infinite width, but no, the effective width is 1 here also, that's sigma. So here width is half width, right? Effective width is 2 actually. In this definition, effective width is 2. So it's a smooth estimator. So k nearest neighbor estimator is we will be using this this kind of estimation, and we'll see that the nearest neighbor computation can further give a more adaptive flavor of this computation of this density function. So we'll see that how we can adapt. That means here we will be seeing that we are not working with a fixed weight. We are working with the kind of variable weight. If the region is very dense, then weight will be smaller. If the region is sparse, then the weight would be larger, because you are considering the span of the certain number of nearest neighbors, right? So your weight is dependent upon the corresponding span. So distance in an univariate case is represented like this. As I was mentioning, that kernel is a function of distance, which is very simple. Just take the absolute difference of 2 points, 2 values of random variable. That is what is distance. And because it's univariate case, right? Usually the distance is used that Euclidean expression for any n-dimensional case, and you can see this is also a special case of that expression in a single dimension. Now, so we consider that this representation notation that dix is the distance of the ith nearest neighbor from x, and so this is what I was telling you, that how the width becomes adaptive. This simple diagram just shows that if I consider the point of the random variable x where you are trying to estimate this density function, and we also sometimes refer it to as a query point, right? Query point in your input space. So in unidimensional variable, it's sorry, it's simply the continuous variable real axis, real values it takes. So we can simply explain in terms of a line graph, line diagram, where a point on that line, straight line, that is representing the corresponding real axis of that random variable, that domain. So that is x, and those are the boxes which are showing the other sample values. And we consider that k nearest neighbor values following the definition of distance, as you understand. So the kth nearest neighbor is the farthest nearest neighbor within that k number of nearest neighbors. So which means kth nearest neighbor. So if you consider that is your the distance is dkx, say according to our definitions of probability density functions, what we have considered, the width of a density function we will be estimating considering this particular weight. So 2 dkx is the weight, right? So this is how it is adaptive, because in a data point where you have sparsely placed input samples, naturally this distance will be larger, where for the densely spaced input sample, this distance will be smaller. So your density function estimation becomes further refined and robust. So how do you compute this k nearest neighbor density function? So a very naive estimation could be like this. That is a naive estimator. Do you agree? So k is the number of times, that is what is k nearest neighbor. That is the parameter k, or hyperparameter k denotes here. K is the number of samples around x, right? Within that width, 2 dkx. Is it clear? So your probability density will be k by n into 2 dkx. Do you agree? So when you are not using this kernel function, so this k nearest neighbor density estimate is like naive density estimate. Only thing is that your width has become now adaptive. But when we consider it is already adaptive, but no, we can use also kernel estimation. That means kernel function. Then this function, similarly, it looks like this. The same under the same framework. So you can use those corresponding functional forms like Gaussian or box function, what we discussed, normalized box function and normalized Gaussian function, that you can use also to do the estimation. So this is what you will be doing for computing the probability density function. Is it clear? This is for the univariate case. Is there any doubt? So now you can tell me that no, how actually you are going to use it for computing the posterior, or let me say for computing this a likelihood first. How are you going to use it for computing the likelihood for an univariate case? So I have just given you a general framework for computing the density function or probability density at a particular point x, right? So if an observation occurs x, suppose random variable, a new observation has occurred, say I represented it like x. So how are you going to use it? How do you compute the likelihood? Any idea? So somehow you are missing some of the points. Oh, I have used, I have to, why, anyway. There is some problem, no? I have, okay. I'm not getting these things. So any answer to that? Somehow I'm not getting the participants list. So let me ask then, Utkarsh, can you tell me? Any idea? Okay, got it finally. Okay, so let me proceed. See, the thing is that you will be doing it, you will be observing the class-specific occurrences for likelihood. The same thing, you just extend it. You find out for every class, how many times, so for every class, what is the distribution of this random variable? That you observe. Anyway, this system is no, is not working properly for me. Right. So that will be considering the same density function estimation. You do it individual class-specific density functions, and then that would give you the likelihood. And uh, you can also compute the priors of every class by using the simple frequency by simply counting that number of times a class occurs in your sample set and what is the relative proportion by which you can get the priors of classes. And both of this can give you the posterior part. Should I explain it a little bit more? So what I am saying that this expression for density estimate, you consider what is the probability of X given a class, say C1. So given a class C1, you are doing the same, you are computing the same. Only thing is that you simply consider only those observations of random variables within this class. Then you can apply the same thing, same computation. Even this one also. Either this one or this one. Either this naive estimate or you can use this kernel estimator. And you can compute this. So for every class you can do it. And similarly, you can compute the prior of the class by observing your input data set, training examples. Because in the training examples, you have the corresponding, what it is giving. In your training example, every example, XT, will have also its levels, right? Which I have not mentioned here. But as you understand, it is under a supervised classification framework. But so you should have both the things. You should have the input data, that is occurrences, and its class level. So this observation, this is used for computing both likelihood and also for computing prior. So product of these two, right? So this product is useful in comparing the posteriors, because no, you are not computing though you can compute also density function. No? You can also compute probability of X, which is independent of classes. That means overall, in the overall training set, again, you can use the same. So this is giving you the corresponding posterior values. We'll come to that point once again. But this is that simple concept that is used for computing the probabilities and use it for the classification. So this concept could easily be extended in multivariate density estimation also. Because as you can see, we are simply considering the neighborhood relation. So the distance function is modified in the multivariate space. That means in the d-dimensional space in this case. As you can see, our random variables, if it is an element of a d-dimensional space, so you have to use a d-dimensional distance function in that space. For example, Euclidean distance in that space. And you can again define the kernel function, because kernel function is the function of the distance function. So there is nothing much, nothing. It is very trivial to extend the kernel function of univariate cases to the multivariate cases. That is the advantage you have. Only thing is that you can see here, that is interesting to note, that while estimating the probability density, you are considering, instead of an interval in a linear interval, you are considering a hypercube in the d-dimensional space of width h. So it has the volume of that hypercube is h to the power d, and so that is the density function should take care of this part. Okay, so this is how you are computing the probability density value at x, and rest of the things are pretty simple. that is the simple extension what I mentioned. Of course, this is the property of the kernel function that I mentioned, that no, its integral should be 1, and kernel function could be as simple as a simple Gaussian function, because it's a function of distance. So you can use univariate Gaussian function also, but you can use also multivariate Gaussian functions. Like you can use this also as a distance function, and which means that you are using Moll-Lewis distance function in that case. And for discrete input, you can use Hamming distances. So these are different cases, but you see the concept is same. Only simple definitions, variations on the kernel functions, your computation would give would be applicable in that context. So that is the simplicity of this particular concept, but it's very powerful. And finally, you can see that no, it is reducing to a very simple computation for classification. So what is that simple computation? Let us understand. You can here I have provided you the training examples, as I was mentioning, that there would be two information. One is the corresponding any query. Okay, so one is that input sample and the other one is the class level, but class level also can be considered as a vector of that is it's an m-dimensional vector, you can see m-dimensional, because m is the number of classes. It's simply the mathematical representations. So ni is the number of samples in class Ci. So that is what we are considering. So which means that if you are considering k nearest neighbor, first is the probability of Ci, likelihood, sorry, prior of Ci is simply computed as ni by n. Okay, so that is what I was mentioning. Simply you count the number of occurrences of that classes in the whole training sample, and then the proportional value or its its normalized value with respect to the total number of samples. That would give you probability. And whereas you can compute the likelihood value in this form, right? So here you are considering only those xt which belongs to the class Ci. So that is taken care of this product. That is taken care of this product RIT. It is taking care of that. So that is why it is represented in this form, so that you can have a very nice mathematical elegant representation. But essentially it means only those kernel functions in the context of that classes only. So if the sample xt belongs to a class Ci, that would form that kernel function. Otherwise it would be 0. So that is what. So that is how you compute the likelihood value of the corresponding sample, and then your discriminant function, I can again explain in terms of discriminant function. It is basically a product of likelihood by prior, likelihood and prior would be like this. So this is your discriminant function, because finally this ni and ni gets cancelled. You can see this in probability, this part is this one, ni by n, and here in the numerator, in the denominator you have ni. So this and this gets cancelled. One is in the numerator, another one is the denominator, and this gets cancelled. So finally this n takes place here. So this is what your expression for the product of likelihood and the prior, and you can use it. You can use this expression for your classification. Also, you can say that actually this is a common factor which can be ignored. Now, when we consider the KNN estimator, we are not using the naive estimation. That means the interval is not uniform. So we assume it's an adaptive volume, which is given by this V superscript kx and volume of hypersphere. and then the posterior Ci can be written in this form, so which is basically Ki by K, right? That is the simplicity. So what is K? K is the number of K is the K. Basically K is that K nearest neighbor, number of nearest neighbors that you are considering around the sample X in the input space. And what is Ki? Ki is the among them the number of nearest neighbors which belongs to class Ci. So if I take these ratios of these two, Ki by K, that is actually giving me the posterior. Very simple computations. So you see that it it has a very strong Bayesian theory behind it, but the computation is pretty simple for K nearest neighbor. For you assign that class within that K nearest neighbors, the class which occurs, if I use a MAP policy, maximum a posteriori policy, the class which occurs maximum time you assign, and that is mostly used, maximum a posteriori policy used. Otherwise, what you need to do, otherwise, if I consider this is the class distribution, and what is the expected value of the class? What is the expected value of this class? Otherwise, you have to consider. Right. So this is what is the K nearest neighbor computation. Actually, this is this maximum a posteriori probability consideration is there for K nearest neighbor, and we just find out the maximum times which neighbor has occurred, which class has occurred within that K neighbors. So the flavor of this K nearest neighbor computation can be further generalized in a class of instance-based learning. Here I'll be going beyond this Bayesian framework. I will be considering the framework which is a kind of instance-based learning is a type of learning framework. I mean, which can be explained under some of them can be explained under this Bayesian framework, and some of them has its own flavor. The idea here once again is that it is the same. When we started with non-parametric approaches, I mentioned that the non-parametric approaches are mostly used for instance-based cases. When you are having training examples, for each example, you are using it in the estimation of your probability density functions, etc. So here, the idea here, it is already mentioned that the task of training in the instance-based learning is very simple, because the problem is posed in such a way that if I give you any unknown instance, you try to find out what are the similar instances which are there in your database, similar to that instance, and then you consider that what kind of labels they have, and based on that you take a decision. So these nearest neighbors are that similarities. It is reflecting that similarities. It's the same thing. Only in a bit generalized way, I can say that you retrieve a set of similar related instances, and then you either classify, even you can regress, or that means you can determine the functional values. You can determine the functional values, not only discrete functional values, like class levels, like a discrete functional values. It could be continuous functional values also. That is what the task of regression. So that you can also approximate. So if that is the form of your target function, you can try to achieve that target function using this kind of instance-based learning. The advantage is that if your target function is very complex, then it is very difficult to model those target functions with certain algebraic form, parametric form, with some hypothesis, with certain constraint, by constraining with certain kind of hypothesis. It is very difficult to put those constraints on the form of those functions. So if the form of those function is difficult to comprehend, to guess, so there you will see this kind of instance-based learning has its advantages because you do not require any form of this target function. Uh, it does not consider any global form. What it does, it computes locally. You can see that k nearest neighbor is also an instance-based learning because it computes the local occurrences around that uh, instance, around that particular query point. What are the instances around that, local instances, and using them only, depending upon their class levels, it is simply assigning a label, assigning a class to that particular instance, sorry, to that particular query point. So these are examples. Similarly, there is another kind of technique which is known as locally weighted regression technique, which I will be also discussing soon, very briefly. So there also you will find an example of this. And I mentioned this term lazy learning because this is one of the characteristics of this instance-based learning. This is lazy because your learning is delayed until a new instance gets classified. And instead of computing once for all, what you are doing, you are computing incrementally. So all these flavors are there. So I talked about KNN classification. Let me extend that idea to KNN regression. So here you see that in a regression problem, your target function is in the form of a continuous function. That means the values. Its range is in the continuous domain. It's a real axis in this. So this is the form. From a d-dimensional input space, you're mapping it to a point in the real space. So a continuous function in that sense. If it is not also continuous, I should say domain is continuous, range is continuous. So again, your data is in this form. Like your training examples have the functional values that is being observed at a point, sample points, and you would like to estimate the value of fx given an x. So once again, from the KNN's perspective, I am defining the ith neighbor of x as xi, and then it is very simple that if I have k such neighbors, k nearest neighbors around x, simply you average their functional values. That would give you the corresponding estimate. That is the, I should say, a very simple approximation using k nearest neighbor policy, and you can make it weighted also. So you can make this averaging and weighted averaging. For example, weights could be proportional, inversely proportional to the square of distances, or you can use a kernel function. You can use a kernel function as we discussed, and there the weight should be proportional to the kernel function. So which takes care of that uncertainty around every observation, and you are giving some weights around it, where the maximum weight is put at the point of observation, but it's in its vicinity also there are some weights, positive weights that we are doing. So that is the example of extension of KNN regression. And let me then also discuss another technique called locally weighted regression, which you will see that it also considers the local neighborhood structure and the functional distributions around that neighborhood, and tries to approximate the functional form using that information only. So in this case, the target function, we are considering a simple form like linear form. Of course, this is a this is a kind of constraint we are putting here, but in a general discussions, you may have a polynomial of degrees, any general degree of polynomial. That also you can consider, but usually from this perspective, the linear form is used. That is more popular. So the linear form, as you can see here, it is just example is shown. So there are d-dimensional, input is a d-dimensional entity. So you have a functions of these different attribute variables. They are the variables, they are the components of the observations. So there are d+1 terms in this function. So once again, a regression problem, as you can understand, that mean squared error technique is mostly used, which means at my hand locally, I have the information about either locally or globally, whatever, information about certain points. And then if this is a functional form, I want to fit these functions with that observation set. So that is this very classical mean squared error estimates. But with respect to locally weighted regression, we consider there are three scenarios. Like we are considering the nearest neighbor scenario. So we'll be only concentrating our observations over those k nearest neighbor mostly. But we can also consider the observations outside the k nearest neighbor zone. That means all the samples, but with certain weights. That means weights will be decaying as it proceeds. As it is away from the query point. So those samples which are at a distant places, they should have less weight, and it should be decaying. It should be almost zero if it is very far. So that is the kind of scenario. And other scenario is that just don't consider them at all. Only restrict yourselves to the k nearest neighbor samples, and then you have the weight distributions among them. So this is that particular expressions. What is showing that it's a weighted mean squared error scenario expression, and that we are using. Can you tell me why this half is there, 1/2? Any idea why this 1/2 is inserted here?
To avoid double counting.
Double counting? No, it's not like that. Actually, it's from the algebraic point of view. If you differentiate with respect to these coefficients, what are you going to do? Mean squared means you are trying to differentiate with respect to these coefficients, individual coefficients, W0, W1. That is what you are trying to find out. You are trying to find out optimal W, which will minimize this error. So partially you can make partial differentiation, and since it's linear form, so what you will get that this is a quadratic term. So these two will be cancelled if it is multiplied with half. So it makes your derivative expression simpler. So that is the idea. So as I mentioned, you can have unweighted kn's where this kernel is equal to 1. Kxtx is equal to 1 just at the point xt, otherwise it is 0. And you can consider weights proportional to this kxxt and over kn's with weights proportional to kxxt. So weight update rule is this. I am not going to discuss the reason explanation. So we'll be soon discussing all these particular gradient computations. So it is this expression comes from the gradient descent optimization technique, and those who are aware of these techniques, they can easily understand that what you have to do, that you start with an initial weight, then at every point you update this weight, and you go on updating, still your error is getting minimized and stable. So that is what is your point. So anyway, so these are the things which we just considered and we discussed. So let me summarize this part of my topic, that is non-parametric approaches. As you can see that it is essentially means that you are estimating the probability density functions using certain kernel functions on a local support, and this kernel has this should have this property of the bounded integration with 1. The value should be equal to 1. It requires, of course, high computation and storage. That is the kind of disadvantage of this scheme, but it is very simple to implement, and also it provides very good performance on the average. It can be modeled as instance-based learning. There are different techniques to address this issue of computation and also storage. So those challenges. Those challenges are also taken there are certain some other methods, advanced methods by which you can take care of them. So other thing is that we have considered that even the regression problem also can be handled using this kind of non-parametric approaches or instance-based, I should say instance-based learning approaches were that we discussed here. So with this, let me conclude this topic.